everybody, my name's Phil Edwards. I've been a developer and a trainer for a number of years now. I've quite a lot of experience, and I've got a really strong belief that software should be built to the highest possible quality. And part of the process of this particular course is looking at that. How can we improve the quality of the software that we have in production so that we don't have any serious problems? I've done the OMG Fundamentals certification, but I've been, say, a senior developer, design engineer. I've done quite a lot of roles over the years.
My name's Randolph Kale. The path to becoming an authorized instructor is fairly straightforward. First, you are certified. I have over 40 years of experience in the IT industry, both on the technical side and the management side. My role with various clients is as an architect, designer, developer, team mentor, trainer, and a consultant. I've been involved with several companies, both training companies and major software providers. I have a degree in computer science. I was very fortunate also to be involved with the early adoption of Java.
Hello and welcome to DevOps Practitioner Lesson 1, DevOps Overview. In this lesson we're going to be looking at what DevOps is all about and why we need it. So what are we going to cover today? Well, first of all, we've got to get an understanding of DevOps. What is it? It's very difficult to describe. Get an idea of the technical challenges of DevOps, which are quite a few, and how to choose the right tools to use, because there are plenty of them. How to choose when to deploy an application into the cloud rather than on a local machine. And a very important understanding of security issues. We also need to understand the difference between requirements and architecture, which are often confused. And we also need to be able to write good acceptance tests. Okay, so what is DevOps? Well, first of all, we're going to find out what this actual term means. DevOps is short for Development Operations. It focuses on a collaboration between developers and other roles. Developers typically work in isolation. They can't do this anymore. We need to work in conjunction with the operations people and the QA people. We need to find out how to develop an application from start to end, from the inception all the way through to production and production support. It's about thinking about how things are going to work in the future when we're in the very beginning stages of the operations. And also the great importance is on automating the process. We don't want to do things manual anymore. We want everything to be fast, totally automated and reliable. The number of issues facing DevOps. Software requirements are constantly changing. We also need to define a good path between design, development, testing and release. We need to decide how to package the software, how to distribute it and how to deploy it into production. And we also need to have ongoing operations and running the system from the future from once it's deployed onwards. There are a number of deployment issues. These are particularly true in the case of web applications. Traditionally, developers write the code and operations people manage the servers. When it comes to things like application servers, there's a gap because there's a thing called a deployment descriptor which is neither in the developer's realm nor the operations realm. We need people who can bridge that gap if we're going to be successful. So because developers have very little knowledge of the application server, they only know about the code and they're only interested really in the code. The actual workings of the application server can be a bit of a mystery. The operations team are not usually developers, so they don't know how to interface the software with the application server. So we need people who are both developers and operations people to resolve the issues. This is what DevOps is partly about. Now, the whole process of DevOps is to use automation and use different tools to do the operations. There are a number of different categories of tools. Each of the categories has got its own range of tools which each do something similar but in a slightly different way. So for example, we've got tools for monitoring, we've got tools for releasing into production, configuration management, packaging the application, all sorts of testing, integration and performance testing, building the application and initially starting with the code development and unit testing. So the whole range of tools, and we'll be looking at the whole range of these tools from one end to the other. So, what are the goals of DevOps? It's about thinking about the whole system, the whole process from start to end. This involves coordinating with the teams and involves having feedback loops from one position to another. It's also about continuous improvement. We need to improve the way we work by working well together and using the tools correctly so that we have fewer incidents in production which have costly repercussions. We also want to improve the process efficiency so that the team learns and is better and better each time. So, some important improvements are these. Reducing testing time. That doesn't mean reducing testing, it means reducing the time that the tests actually run. Try to reduce the amount of changes required. When the requirements are conflicting or incomplete, we need to resolve those conflicts early on. We need to find the simplest solution to meet the requirements. It's not necessarily the optimal solution, but a best solution that works well. We need to use standard tools across the organization which integrate well together. We need to have really robust production systems which have very low maintenance costs and are very, very reliable. We also need to produce software to the highest possible quality. And to achieve this, we need to improve the performance of the individuals and the teams and how they work together. Now, part of the process of improvement is changing the way people work. We need to strive for clarity. We want to challenge any uncertainties in requirements. We don't want to fill in the gap, which many people are tempted to do. Ask somebody who knows what the answer is before making any assumptions. Assumptions themselves are particularly difficult to deal with. We need to be sure that they are valid assumptions and that they haven't been put there for some reason which hasn't been justified. We want simplicity and reliability. The optimal design is almost impossible, but the best design is what we'll strive for. We also want to reduce risk. We need to be able to meet the requirements with the least risk path. And an important thing is to avoid gold plating. Don't put extra code in there just for the sake of it or for some potential future change which may never happen. Do the minimum to get the thing to work. And when there's an issue, find the root cause of the issue. Don't just try and fix the symptoms, because the root cause is going to come back and bite you later on. So the working practice should be constantly evolving and very iterative. So you learn something. Some new technology, some new tool. You try it out. Work with it. Then you think about it. Okay, did I do a good job of this? Could I do a better job of this? How could I do a better job of this? And then you learn some more to improve yourself and go round and round the loop as you improve as time goes on. So that's the end of that section, and now we've got a knowledge check. Now we're going to look at the technical challenges, of which there are many, and DevOps is really here to help solve these technical challenges. So what are these challenges? Well, first of all, technology is constantly evolving. If we look at the IT world, in terms of software itself, very little has changed over the last 30-40 years. We've just got better at it. But the technology has changed dramatically. No longer have we got large rooms full of very hot, expensive machines. We have very small, fast and efficient machines these days, and we have to be able to use this technology to its best. Our working environment is changing as well. We've learnt over the time how to do things better, and we've got more interesting working practices these days than we've ever had before. Good practices 5 years ago are now considered bad practices. This is constantly evolving. There are also external influences over which we have no control. A news story can cause major economic incidents. There are legal effects. Some industries, particularly the finance industry, is very, very tightly regulated. And there's also social influences as well. We need to keep our customers happy at all times. So DevOps is a culture which we need to build and maintain. It needs to adapt to continuous change by continually changing. And the organization's culture needs to evolve around it. The problem is, people are very resistant to change. They don't like to have to do something in a different way to which they're used to. But also, we need to get people to work together and not in isolation. Some people do not like this. They like to work in a box, quietly sitting there with their headphones on, not interacting with anybody, just focusing on their work. We really can't do this anymore. We have to work together. We need to talk together and get together to get a good solution as a team. Now, software tools are very important for the whole process of DevOps. Now, individuals and teams will have their preferred tools. In a large organization which has been formed by mergers and acquisitions, the teams will have come from different parts, and they will have their own different set of preferred tools. really can't do this. We need to have a standard set of tools across the organisation. Open source tools are readily available, although some organisations don't like to use open source tools because of support issues. But it's also important to have a very standardised set of tools across the organisation for various reasons. So look at the reasons. First of all, licensing and compliance. And many of the software applications and tools require licensing. That can get incredibly complex for a big organisation with a very wide range of tooling. We also have problems with versioning. If people are using different versions of the tools, there are going to be compatibility issues, which you need to address. There's also very important that there are production support for the tools. You can't introduce a tool into a production environment if the production support team can't support it. And we also need to think about the future. Once an application is in production, it needs to be maintained and supported, and it needs to be easy to do that. So many organisations have legacy systems. And any new tools which are introduced need to be able to function with both the new and the old systems. We're getting to the stage now where we're getting hybrid environments. We have the existing solutions, we've got new cloud-based solutions which are increasingly attractive because of the cost values, and tools must be cloud-ready or cloud-compatible for future deployment. The old and new systems need to work together and complete with production support for both old and new systems. Corporate networks are very important, and they're getting increasingly complex. We need to address issues such as internet connectivity. We need to think about the addressing of various machines and firewalls. We need to have virtual local area networks across sites. We need to connect to the cloud. How about the data centers? Where are the data centers and how do we connect to them? And also think about the local area networks on the company sites, keeping teams isolated from each other so that they don't have access to each other's data if that might not be a good idea for various reasons such as security. So changing the network configuration is very complex. It's also very risky because you're likely to break connectivity. Cloud computing comes with its own networking, which is actually very efficient. It makes things less complex, much more adaptable, and more auditable. It also needs to be more secure, but cloud platforms are very secure by default. Everything is denied by default, which is always a good thing. You have to open up access to give people permission to do things. There's also a cost impact. Changing corporate culture is costly. We need to buy new hardware. We need to buy new software licenses. We need to pay for cloud usage, which is usually by resources like CPU and network. We need to retrain our employees so that they understand and use the new equipment and tools very well. People are learning new skills. We do run at a reduced efficiency, but we have to live with that. So there needs to be a budget for ongoing change. We need to know it's going to cost. There's going to be an initial cost in terms of efficiency and quality, but that will improve over the long term. So DevOps is not just about writing and deploying code. We need to improve existing code. New tools need to support new code. New tools need to support new code, but they also need to be able to support legacy code. Legacy code might need to be changed or restructured over time to make it more manageable and to make it fit in with the new process and tooling. And we need to take on board bug fixing enhancements, which need to work with the new tools and new procedures. Now, so let's have a look at some of the software tools. We'll be looking at each of these tools in more detail later on during the course, but let's have a look at what the actual basic tools are. So we have the concept of a tool chain, and one of the challenges is to select the right tools. There are many tools that perform similar functions, and the tools also need to work very well together. And there are a number of categories of tools, for each stage of the software development lifecycle phases. Some tools straddle various phases, some are very specific to individual phases. So let's look at the first stage, which is requirements analysis. And it's all about communication within the team and talking across different roles. So we need to be able to allow developers, managers, customers, business analysts all to talk the same language. And think about the various tools that we want to use. So fairly obviously, word processors and spreadsheets, although spreadsheets are often very much abused and can cause a lot of problems. Shared calendars, so we know when meetings are. Sprint management tools, although a lot of sprint management tools are very low tech. Wikis are incredibly useful for storing information which is readily accessible. We need UML diagramming tools to describe our applications, and we need issue and task management tools to manage the workflow. We have the concept of artifact creation. An artifact is simply a byproduct or result of some operation on some kind of code. So very important to source control systems. They manage the versioning of our code and make sure that we're building the right thing from the right versions of the software. We've got continuous integration tools, very important for detecting problems early so that they can be fixed and so they don't delay other developers' work. We have build tools which assemble the components of our software from source code through the various artifacts to the production executables. We also need to gather documentation information, and there are tools that do that. The most complex stage of any software development is the code development stage, and there are many tools that are needed at this stage. There's a variety of different editors. We need different databases, different types of databases, different tools for building the software. We need tools for code review. There's also very important code quality tools which can assess the quality of the code and identify common problems very quickly. We have various things like REST API design, and that's a very difficult thing to do. Develop an API for communicating across a network using the REST APIs is very, very difficult to coordinate. User interfaces are also incredibly difficult to describe and get to work well. We also need to be able to map code to databases. We need unit testing and mocking frameworks to make sure that our code is fully custodied. The very important integrated development environments, they save a lot of time. Developers effectively have an operating system for which they can develop code without having to go outside of it. And then, of course, we've got the compilers and interpreters which tend to just work behind the scenes, turning our code from source code into executable code. Testing is vitally important. We start off with unit testing and mocking frameworks for doing test-driven development. We've got scripting for writing more advanced tests, such as integration tests. We've got test harnesses which test full systems and partial systems. And we've got user interface playback tools for testing web interfaces. We've also got packaging tools. We have repositories where software is stored which we can fetch and integrate with our system at any time. Build tools appear here again. We've got container management tools which are increasingly important. People like the use of containers where you have one application per unit of deployment which can communicate with each other. And then we've got the deployment descriptor generation tools, which is also very important because deployment descriptors which describe how software interacts with containers are very difficult to write. Then we've got release management tools, which are also very important. Change management systems. We don't make change into production unless it's been fully documented and approved. We need approval systems to approve releases. We need to have important rollback mechanisms. If we deploy an erroneous system into production, we need to get back to the previous version as quickly as possible. We need to automate the process of release. We also need to be able to schedule tasks so that we can run various components of the system at the right time and in the right sequence. And the important enterprise integration tools which allow us to deploy and change applications dynamically, automatically. Very important configuration and monitoring tools. Infrastructure configuration and management. We don't want to do it manually, we want it automated. We have the concept of infrastructure as code, basically scripting which controls the infrastructure. Request tracing tools. Find out exactly what happens when a request is made, is it being executed and put into production. Performance monitoring is vitally important. Make sure our systems are doing what they're supposed to do in a timely fashion. Also log file analysis tools. Many systems produce a lot of log files. The output is very, very verbose. We need to look for the interesting things, which are usually things going wrong, which are very small parts of the logging. Then we need to be able to report issues as soon as we can detect them and have the processing mechanism in place to deal with them. So now we're going to look at cloud computing. It's getting increasingly important to deploy things into the cloud, as the cloud gives us many benefits, including cost and performance. Traditionally, companies had data centers, but data centers are very expensive to run and maintain. For a start off, you've got to have a building, and the building needs to be maintained, and it has to be purchased. We've also got to buy vast quantities of computer hardware. That's expensive. We also need considerable power supplies. Large data centers consume vast amounts of power. And anything that uses vast amounts of power gets very hot. So we need a good cooling supply to do that. We also need physical security. We don't want people getting into our data center and causing problems. We need to make sure we can connect to the data center from anywhere in the world that we need to. We also need to have maintenance teams to support everything because hardware fails fairly frequently and we need to get it fixed as soon as possible. We also need to have security teams in place to check that everybody's got the right access and nobody has unauthorized access. But that means we've got to have policies and mechanisms in place to secure our data centers. So it's a very expensive thing to do. To give an example of failures, the standard SATA hard drive has got a mean time between failure of 1.2 million hours. That's a long time, it's several years. But if you think about it, a data center with 100,000 hard drives, the laws of statistics, if you multiply those numbers together, it says you can expect 2 drives to fail every day on average, which is quite staggering really, isn't it? Most people don't expect hard drives to fail, but if you've got hundreds of thousands of them, they're going to fail. So what have you got to do? Well, for start off, you've got to have a supply of replacements to replace them quickly. Every disk needs to be mirrored so that if it fails, it's taken over by another one. We need to detect a fault and be able to find it. If you've got a data center with 100,000 hard drives, how do you find the one that's failed? We need maintenance teams who can deal with these problems, locate the faulty drives and replace them. We also need to be able to destroy the disks correctly so that data is not gained by other parties. For example, destroying the disks completely so that all data is definitely lost. So rather than having a corporate data center, we move to the cloud. What happens is cloud platform providers have invested very, very heavily in infrastructure. So what they've got are very, very large data centers, very highly scalable environments, very secure and very reliable. And they provide a number of services. So on a cost basis, you can choose how much disk storage you want. You can decide how many CPUs, how much computer power you want, what services you require, what platforms you want, particular operating systems, and also what applications you require. So one thing that these cloud providers do is focus on doing one thing very well. They provide a computing platform. They're not interested in anything else. It's the users that provide the rest of it. So a bit more about data centers. Cloud providers have very high-performance data centers. They are geographically distributed around the world. It is actually quite important, this. Some organizations are required by law to have their data in certain places geographically. So data centers will be distributed typically several per continent. You need to have access points in many locations. We need to have high-speed networks connecting from wherever you happen to be to the data centers. Within the data centers, there needs to be extremely high-speed fiber cable connectivity between the machines. And many cloud vendors own their entire infrastructure across a global network. They also have edge caching, where information is stored at the boundary where the users interface to the cloud rather than deep inside the cloud where the actual data is stored. So there's a concept of infrastructure as a service, or IaaS. This is the basic power that is provided by the cloud providers. So you've got raw computing power. Choose how many CPUs you've got and what power CPUs you've got. Raw storage, how much disk space do you require? What kind of networking do you require? Do you require an external IP address? And then the ability to build a computer or network computer virtually. You provide the parameters in a web page and the system will just build you a computer within a matter of minutes. So obviously the cloud providers want payment. And how does this work? Well, typically payment is by resource. So when you use a component, nobody else can use it, so you're tying up that resource. So basically it's fair to pay for components when you're using them or when your resource is held. Because if you're not using them, nobody else can use them. But the one thing is, it's very easy for the virtual components to be returned to the cloud vendor. Basically, you choose to have a component and then you release it. So a good example for a cloud is an external IP address. These are very short in demand. You say you want an external IP address for your computer. It's allocated when you start the computer. When you stop the computer, the IP address is returned to the pool for use by somebody else. It's so easy to reconfigure for smaller or larger computers. So now we've got the concept of Platform as a Service, or PaaS. And what this is pre-configured runtime environments, typically operating systems or operating systems plus well-defined applications such as web servers. And these components are cloud-based, and you choose which ones you want. The cloud provider is responsible for updating the hardware and the software to certain versions. So obviously they will only support certain versions of certain operating systems and certain applications for the maintenance purposes. The customers provide the business logic. You provide the code that uses the actual application, the cloud provider provides the rest, and you just pay for the resources that you're using. Software as a service. This is where you get a full-blown application, such as a web-based application, maintained by the service provider, and you pay for the usage. You pay for the networking traffic used, storage information, and other things. Now that you've understood the concepts of IaaS, PaaS, and SaaS, Randy will help you with the steps involved in setting up and examining the cloud-based virtual machine environment for the help of a demo.
Welcome to DevOps Lesson 1, Lab Exercise 1, Cloud Setup. We're going to show you how to get an account set up with Google Cloud Platform. That's the platform we're going to be using in this class. And you have a little time to get some things sorted first. You're going to need a browser, Microsoft Internet Explorer 11 or later, Microsoft Edge, Firefox, Chrome, or Safari after version 8 is just fine. However, Safari private mode is not supported, and I'll be using Firefox and I'll be using a private or incognito window. I'll explain why when we get to that point. So you're going to need a credit card, a debit card, and that's for identification. Google doesn't want to charge you anything. In fact, once you set things up, they'll turn around and give you a $300 credit on your account. That's good for 60 days. All right, so let's start up Firefox. And I find it really important to have a private window. So let's use that. And the reason is that eliminates all sorts of historical cookies or any kind of state that may indicate a previous connection or relationship with Google, and it can get things confused. So I do strongly recommend that you use this approach. console.cloud.google.com/free trial. And that will bring up this screen. It says one account, all of Google, and it says enter your email. So if you've got an email, go ahead and put it in there. And I'm going to say create account. And that's going to go over here. We'll do a email address in here and get a new Gmail address. So I'm going to put in my information because there's a lot of private information here. You're going to see the next screen. You're not going to actually see this being filled out. But I will show you here. You can say, I would like a new Gmail address. Follow that link if you want to. Otherwise, put in your existing Gmail address. Okay, so I'll see you in a few minutes. I have entered that information and I've said next step, and now you see a privacy and terms. You'll want to scroll down and then click I agree. And then it says welcome. Now we're going to continue on to the developer console. And it says try the cloud platform for free. Access to all the products, $300 credit, no auto charge after free trial ends. In fact, what we're going to do is accept this free trial, but we're also going to upgrade, which does put us in the situation where after the trial is over, you will get charged. And the reason we do that is that gives us some additional capabilities and increased quota on the cloud, which is important for the class. and say agree and continue. Now it gets to the point where you're going to type in your credit card information. So I'm going to also have this blank. You'll just fill this out. And it's creating the project. And now it's complete. So it says, "Hi, welcome. Thanks for signing up for the 60-day free trial. We've given you a credit, and if you run out, don't worry. You won't be billed until you give your permission." So in the standard setup, you don't have to worry at all. You're not going to get charged. So we say, yes, I understand. Now, this is set up with a default project called My First Project, but we're not going to use that. We're going to create a different project. But before we do that, we need to do one other step on billing. So up here in the upper left-hand corner, you see these 3 horizontal white bars. That will cause a tray to pop out from the left-hand side. And you want to go down to billing. And that will take you to the main billing page where you can see you're on a free trial, here when it expires, amount remaining, and so on. Okay, so what do? We have to, this is kind of strange, but you need to manually refresh this page. So however you want to do that, with this little reload page or Control-R or something like that. And when you do that, you'll notice that something else appears, this bar up here where you can upgrade your account. This is where you change. This is where you give approval to Google to charge your credit card or your debit card after the trial is over. So you do need to do that. It changes the nature of your account. It gives you more capabilities. So this is important to do. So we'll say upgrade. It says upgrade your account, read through this, be comfortable with that, and then click upgrade. Congratulations, you have successfully upgraded your account. The next step is to create a project for DevOps. So the way you do that is you go up to the blue bar and you'll see there's My First Project. We'll go down here and say Create Project, and you'll get a dialog. You're going to use, actually you can use whatever name you'd like, but we suggest that for this work you say DevOps, DEVOPS. And then you'll notice at the bottom you're given an identifier. This is the project name and this is the project ID. It's synthetic, and if you don't like it, you can edit it and put something else in there. The one requirement is this ID has to be unique across the cloud. That seems fine to us, DevOps-155318. So I'm going to say go ahead and create. So it's going to create a completely new project for us. And this will take a few moments. There's a lot of machinery that Google has to set up, billing, quotas, and that sort of thing. We're done. The next step is optional but strongly recommended, and that is to go in and delete this first project. And the reason I recommend that is if you create more than 3 projects, you risk having your account locked by Google. You're allowed to have 3, but I have found in some cases their monitoring software is a little aggressive. So I suggest you have absolutely the fewest number of projects that you need. So let's delete this first one. We're going to view the projects, let it come up, and then go over here to these 3 vertical dots. Click on that, go down to Project Settings, and then go down up at the top and say Delete Project. You don't actually delete it. You schedule it for removal exactly 1 week later. The entire project will be scheduled to be deleted after 7 days. So you have to type in that unique identifier. So this is Booming Tooling for this particular one. Yours will be different because it's synthetic and it's just generated. And notice the numbers are the same. They tend to stick on the numbers and change the words at the beginning. So it's matched. It's allowed the shutdown button. So we click on that. It says Shutting Down Project and it's pending deletion. If you click on this, you'll see that you have this one scheduled for deletion. So we'll go back. We'll pick DevOps, which is the project we want to work in. And let's just go back to the home area. And this is an anchor location. If you have created resources. You'll see them listed here, and there's going to be kind of an API graph showing you how much compute power you're using. All right, the next step is to create a compute engine instance that's going to be your lab instance. To create the lab instance, we're going to go over to the compute engine area. So we'll go down here, say compute engine, and notice it says it's getting ready. This is going to take a few minutes. It's setting up networking, it's setting up billing, it's setting up quotas. There's all sorts of background setup that Google needs to make. It doesn't do this by default because it is a lot of work, and if a person creates a project for maybe doing big data work or running BigQuery, they're not going to need compute engine, so they just skip that step. So we just have to be patient while this gets set up. It's done. Now we want to create our computer, but we need to take a couple steps before that. There's an image that has been created for you, and I'll show you how you can get to it. There are a couple steps you have to take. The first thing you need to do is activate your Cloud Shell. Okay, there we have our Cloud Shell. The first thing we need to do is create a bucket store in our own project. And the way you do that is you use this gsutil program and say make bucket. And here you're going to have to come up with a unique name. I'm going to give you some tips. You start with gs:// and then what follows must be unique. I'm going to suggest that you say DevOps hyphen your initials, and I'll just pick XYZ, and then follow that by today's date. It's 2017-01-11 as I'm recording this. And as long as it's unique, that's fine. Every bucket has to have a unique name across the whole cloud. So we'll create that. It'll come back and say it's fine. So great, we're in good shape. So next what we want to do is copy over an image that exists in another project. So what we're going to need to do is say gsutil copy from gs:/. Now this you must get exactly as I type it. It is Simplilearn -DevOps -image, and we want to copy everything over to our bucket, gs:// DevOps -XYZ 2017-01-11. That transfer actually took a little while, so I've taken the liberty of editing the video capture so that you didn't have to sit through it. So let's just do a clear here. And we can do some checking. We can say gsutil ls, show us the buckets we have. And then you can say gsutil ls, the bucket itself. And it's just a good check to see what we've got in there. So again, XYZ and today's date. And we see that we've got two tar.gz files. You're going to want to use the one with the latest date stamp. Okay, so now we've done that. We can exit out of the Cloud Shell and now go back here and go down to Images. And we want to create an image so that we can then create a computer. And we'll call this student image. Don't worry about family. You don't need a description. And the source is not a disk, it's going to be a storage file. And we can browse our own storage buckets. So let's do that. And then we want to pick this latest one. So we'll pick that, we'll select it, and now we're ready to go. So we're going to take this as a file in the cloud, and we're going to create a local image that we can then use to create a computer. So let's do that step. Okay, it's done, and you'll see that your image is now at the top of the list. The other images that you see are standard images that are supplied by Google. So this is a custom image that we created, and these are the rest. They just happen to list them all together. All right, we're going to go back to the VM instances area, and now we finally get to create our computer. So this is going to be your own computer in the cloud. This is going to be your lab computer. So you have some interesting decisions to make. The first one, of course, is the name, and I suggest you just call it lab. And then the second one is where it is going to reside. I'm in the United States, and I have an affinity to US Central 1B. US-Central 1 is the region. Notice there's Asia Northeast 1, Asia East 1, and so on. The -B refers to a particular zone. So I'm just going to pick that. You can pick a different one. And notice that the charge is $25.95 a month. Well, we're not going to let it run all month. We're just going to look at the hourly rate. So we're paying 3.6 cents per hour. And that's based on the location and the size. For example, if you go to Asia, it's going to be a little more expensive. Okay, we'll go back to US Central 1B. But you want to pick a computer zone that's near your location because you're going to have a latency between your computer and this one, and you want that to be as small as possible. The next choice you have is how big a computer is it? You have lots of different choices, and the standard is one virtual CPU with 3.75 gigabytes of memory. And that's not a bad choice. I'm going to choose this customize option and actually dial in slightly less memory. I'm going to go down to 2.75, and it drops the price just a little bit. So I'm just kind of doing a little fine-tuning based on my experience. If you want, you can go and have 2 cores and have the thing run a lot faster. And it's 5.8 cents per hour. So again, it's your choice. And I'm going to go back to one, not a shared CPU, but one virtual CPU and 2.75 gigabytes of RAM. Now your next choice is the kind of disk that you're going to boot from. All right, so we need to create it from a custom image, which is this student image. We're going to select that. And then down here, you can say that you want a solid-state drive or a standard drive. Now, obviously, the solid-state drive is going to have better random access seeking, but it's going to be more expensive. And this one is your standard magnetic media. The curious thing here is that the larger the disk that you request, the faster it's going to go. And if you want to set it at 200 gigabytes, then that's about the smallest you can pick and have it really have good performance. But let's see what the price is. So that's going to put the price up to 4.4 cents per hour. So I'm going to go ahead and pick that. As a matter of fact, I'm going to see what a solid state drive of that size is going to cost. So I'm going to select solid state of 200 gigabytes, and that brings it up to 8 cents per hour. Okay, that's fine too. So I want a nice fast machine, reasonable size here, CPU and memory. That's going to be just fine. And then we're ready to create it. So we'll say create. Some of these things you can change later. You can't change the disk, but you can allocate more memory or more CPUs if you find that your machine is just a little bit sluggish. So let's let this create. This takes about a minute or 2 minutes. You know, I thought about this, and I actually want a bit more CPU power. So I'm going to select this and stop the machine. You have to stop it to make any changes. So we'll stop this. All right, the instance has stopped, and now I'm going to select it and choose Edit. And I'm going to go in and change this to, actually I'm going to use 2 CPUs in the standard configuration. So I'll pick an N1 standard 2, and I'm going to say that's the change I want, so I'll save that. And now I'm going to start the computer. Actually, go back out. I'll click on the instance, and I'm going to start it again. Okay, it started. And now we're going to establish an SSH connection to the computer. And we just have to click on this button. It'll create a connection.
So the next section is on information security, which is vitally important. We need to be able to secure our resources. And in fact, it's probably going to be a legal requirement that you engage the information security team at an early stage of your project, and certainly you'll need to engage them towards the later stages. Security is a vast and quite intensely complex subject. What are the security threats to a system? Well, think about things. Physical access. Can people get control of your systems physically? Social engineering, the impact of people. External influences such as crackers. Also external influences such as eavesdroppers and man-in-the-middle attacks. The all familiar viruses and Trojan horses. Buffer overflow attacks are particularly nasty and have caused many problems over the years. As have denial of service attacks. They've taken down entire systems and entire organizations. Human error is a very common problem. Not necessarily malicious, but humans make mistakes. Also configuration errors. If you make a configuration error, it can have a vast impact on the system. And probably least likely are malicious employees. It can happen, but most human interventions that cause problems are done by accident. Two important aspects of security are AAA and CIA, the three acronyms. So AAA, we've got authorization. Are you allowed to access this system? And what access do you have? Authentication. Are you who you say you are? Auditing. What happened and when? The three others, CIA, confidentiality. Who needs to see the information and who shouldn't be able to see the information? Integrity. Does a debit always correspond to a credit? Availability. Is your system available all the time or sufficiently for the requirements of your customers? So there's some important security principles. Information security is absolutely vital. You need to engage the information security teams during development. They're often seen as people to be avoided, but actually they're very keen to be talked to because they can solve problems very quickly. They know the issues. If you go and talk to them early, you can solve problems which will save them headaches later on in the program and make their life easier, so they're very happy to talk to you early on. Security always comes at a cost. Whenever you secure a system, you make it harder to use. This causes a few issues that people like to bypass the security systems to make the systems easier to use, and we can't really do this. So there are a number of security principles which help reduce the risks, and we're going to look at these over the next few minutes. The first one is called defense in depth. The idea of this is you've got various layers of defense. So the idea is that if somebody compromises the first layer, the second layer and subsequent layers are still holding. So an example here shown of a web server, you've got the internet, which is a place where people are likely to have malicious intent. You have an initial firewall which stops a certain number of attackers. You've got the demilitarized zone with a web server which is also hardened. And then you've got another firewall to protect the internal network. So if the first firewall is compromised, then they've also got to get through the hardening of the web server. They've also got to get through the second firewall, which gives you 3 layers of defense. One aspect of defense in depth is associated with cross-site scripting, or XSS. It accounts for over 80% of website vulnerabilities. The idea of this is quite simple. You have a link on a website. The link points to a document which has embedded HTML controls or JavaScript. When you click on the link, the browser loads the page and executes the code. The code can have malicious effect. It can get information from the browser or even from the host computer. So the important thing is never store raw user data. If you have a form where people can type in stuff which goes into a web page, it's possible for them to add code into that form which can be malicious. So what you need to do is sanitize the input of any user from a web page form to remove any HTML controls or JavaScript, or at very least escape it so it can't be executed. Another important aspect of security is to minimize attack surfaces. The idea is that the fewer entry points into the system there are, the fewer vulnerabilities there are too. So the analogy here is the armadillo that wraps itself up in its shell so that there's minimum amount of places where a predator could attack it. So in the case of IT, we've got things like most organizations do not permit the use of USB memory devices because you can introduce viruses through these things. You can also take confidential information out of the site via these devices. So these are things that are included in corporate security policies to avoid some of the problems of having multiple places where people can either inject or extract information. We have the concept of fail secure. This is the complete opposite of fail safe. If you have a locked door in, say, a theatre, if there's a fire, the doors will automatically unlock so that people can escape. So that's a fail safe. A fail secure door would actually lock in the case of emergency to prevent people getting in. So systems should fail secure. That's the important thing there. Think about what happens if you've got a store which is doing online transactions. The connection to the credit card validation system fails. What do? You stop the sales. You don't store a partial sale without having got the money from the credit card validation system. This is actually very important, least privilege, and it's surprising how few people actually do it. The idea is you give programs and users the bare minimum amount of access they need to perform their job. It greatly improves. Least privilege is very important. The idea is to give programs and users the minimum amount of access they need to perform their job. This greatly improves security and stability. It requires less testing. It makes deployment easier. So for example, if you've got a backup system, it needs to be able to read the data it's backing up. It needs to be able to write to the place it's backing up to. It doesn't need to be able to write to the data it's backing up, so don't give it access to it. A common problem is security through obscurity. Trying to hide something on the principle that nobody can find it. A typical example is a web server listening on a strange port number like 5267. People think, oh well, if I put the web server on this port number, we know about it, but nobody else will be able to find it. This is not true. There's software out there called port scanners. It'll just scan all the ports on a particular machine, and when it finds something interesting, it'll have a go at attacking it. It'll find your web server. Cryptography is an interesting one. In the early days of cryptography, only government employees knew the algorithms. So the algorithms were effectively secret. Nowadays, all of the cryptography algorithms are public domain. They're well published, well known, and everybody can look at them. So now, the security is not about the secret algorithm, it's about making sure the encryption keys themselves are very secure, not the algorithms in place. The use of modern languages. We understand the root cause of many security breaches, and language design has changed to make improvements. Modern languages make it hard to make mistakes. The Rust language aims to eliminate memory allocation failures that allow hacks easily created with C and C++. C and C++ were particularly bad for memory leaks. The Kotlin language aims to eliminate null pointer errors that can crash systems. REST-based systems de-emphasize the use for any programming because it's all very much decoupled. This is probably one of the most important ones. Keep it simple. A simple solution has fewer vulnerabilities. Once you have a complex solution, you get more complex failure paths. A good example is the mail program SendMail. In 1996, it ran about 80% of all mail servers. But SendMail has a very, very cryptic configuration file. It's highly symbolic. It consists of lots of dollar signs and brackets, and it's very hard to read unless you're an expert at it. Nowadays, it doesn't run anywhere near as many mail servers. In 2015, it was down to 24%. People have moved in favour of simpler mail servers, which are simpler to administer and configure than SendMail. SendMail, in fact, is actually very good at what it does. It's very, very hard to configure. Another important aspect of security is segregation of duty. If you've got a very critical function, make sure that one person can't execute the complete function from end to end. What you need to do is divide the function into individual steps and give each step to a separate person or entity. So it requires the collaboration of all of the individuals to complete the operation. A good example of segregation of duty are the three fates of Greek mythology. They have the job of deciding how long someone lives. Clotho spins the threads of life. Lachesis measures the threads of life. Atropos cuts the thread of life to show the end of the life. Trust and complete mediation. It's important to know the difference. Trust is basically where two people have exchanged some information and they know that each person is who they think they are. And so no further checking is required. Complete mediation is where credentials are checked on every access of the system, often on a time basis. Typically what happens is a token is generated on initial authentication. The token has to be re-delivered at every operation, and the token only lasts for a certain period of time. Single sign-on systems is an accepted compromise. The problem with having many systems, each with separate passwords, is that people have to have many different passwords for each system, and they tend to forget them. This means that the system administrators are constantly resetting passwords. So a single sign-on system is an accepted compromise. You sign on once, and the single sign-on system will authenticate you to any other system. It's a known security loophole, if you like, but it's an accepted one because of the system is completely understood, and there are good solutions out there, and it's considered worthwhile to avoid the complexities of password management. Don't reinvent the wheel. If there's an existing solution, use it. Writing good, secure software is actually quite difficult. And rebuilding software from scratch will almost certainly reinvent previously discovered issues. To give an example, the TCP/IP stack. The Unix stack has been take an example, the Unix TCP/IP stack. It's been around for a very long time. It's very stable and very reliable. Later operating system vendors have actually re-implemented the stack themselves, and they rediscovered many problems which had been detected and solved many years ago by the Unix environment. Passwords are always a problem. Many people have very insecure passwords. They tend to choose things which they can easily remember. So memorable dates, birthdays, people's names, car registration numbers, favourite words, all sorts of things like that, which are very insecure because they're fairly easily guessed. Now, also, passwords are stored as a one-way hash. You take the plaintext password, apply an algorithm to it, which produces a fixed length number, which is statistically fairly unique for the text. So it's very unlikely that you'll be able to find two pieces of text which generate the exact same hash. Unfortunately, there's software out there which can find these things. So there's software such as Crack, which will try a whole bunch of different words based on dictionaries and combinations of words and numbers, and they find most common passwords very easily. There's also rainbow tables, which is where you have typically websites where they've pre-calculated hashes of lots of different passwords up to a certain length. All you need to do is paste the hash into the website and it will tell you what the password is if it finds a match. There are ways of securing passwords. A typical mechanism which is used by Unix and has been for a while is assault. What you do is you generate a random number of fixed size, say 16 bits or 32 bits. You add it to the password and then create the hash. You also store the salt with the resulting hash. So you know what the salt is and you can reverse the operation. So having got the salt, what you do is you take the password people enter in to authenticate themselves, you add the salt to the end of it, and then you generate the hash and compare the hashes. This defends against rainbow table attacks because effectively every password needs to be multiplied by the number of possible values of the salt to generate a complete rainbow table. There are also very good ways of making secure but memorable passwords. One quite easy one is you take two short but unrelated words and put between them numbers and punctuation symbols. So like Bond 42 ! Frogs is an example of such a password. It's quite hard to be able to predict what it is or generate software which can crack that password. Secure ID is commonly used by many organizations. It's particularly useful for giving your employees remote access to your internal systems. The idea is this. The user is issued with a device. It's a small electronic device which contains a clock and a random number generator based on a seed. So what happens is, every minute, the device displays a new number. The number is actually predictable if you know the algorithm and know the time. The server has a clock and a database for the seeds for each of the devices. So the server is able to calculate what value is being displayed on any particular device it supports at any one time. So what happens is the user typically authenticates themselves by entering some kind of personal identification number and the number that's currently displayed on the device. There is a slight problem associated with this. If the clocks between the device and the server get out of synchronization, which does happen, there are ways of dealing with this. The servers can store a drift value so that they can calculate the offsets for between their clock and the device clock and be able to calculate the value correctly. There's also biometrics, using some innate but unique characteristic of individuals. So fingerprints are being commonly used. They're used at airports a lot these days. Retinal scans have also been used at airports, although Heathrow Airport used to have a retinal scan machine, but unfortunately they discontinued it. Now face recognition is getting more common, and a lot of airports are starting to use that now. There's voice prints are also used to identify people, and also each individual types in a different way. The speed of typing and the timing between the keystrokes is unique to each individual, so any of these mechanisms can be used to identify a person with great deal of reliability. Information security. Many organizations have information security teams. Their role is to ensure we've got compliance and to ensure that systems are safe and secure. You need to engage these teams very early on in the project. They are very easily engaged. They really want to talk to you because they don't want the consequences of you introducing a security risk into the system. If you engage them early, they can detect potential problems and fix them before it becomes an issue. Now, as a developer, you're on the front line. When it comes to information security, you have to have more access to systems than anybody else. You are also writing the code which needs to be secure. If you code insecurely, you are going to be the cause of a vulnerability. So you need to understand the implications of security and make sure that you think about it at every stage during the development cycle. Now we get on to the first stage of any major project, which is requirement analysis and the writing of user stories and how we capture requirements. So what are requirements? Well, there are various standards. It's basically what a system is supposed to do, capability or conditions needed by a user to solve a problem. What is required to satisfy the contract? Are the standards and specifications or other formal documents required? And documenting the conditions and capability required to achieve an end result. So requirements gathering or requirements definition is a difficult process. It's an iterative process. First of all, we need to decide what the problem is. Now, problem definition is quite difficult. We then need to be able to turn the problem into a series of requirements. And it's important to note that defining requirements is not the same as designing the system. Designing the system is really how it works. The requirements is purely what it does. The main requirements of interest to developers in particular are function requirements. These are the ones that say what the system actually does. Basically, the condition is this. We have a process which at the moment is a black box. We don't know what's inside the process and we actually don't care at this stage. It'll have an initial state and we apply some kind of input or inputs. Process will happen and we'll get some outputs and the system will be in a final state. That is basically the whole process. Those four things. Initial state inputs, final state outputs. Be careful though, at this stage, if you get it wrong or make assumptions that are invalid, this is where problems get introduced very early into the project definition. Interface requirements define how inputs and outputs relate to other processes. So if you need to communicate with another process or other machines, you need to be able to communicate in the right language. These are often called integration requirements because integration testing is where these are tested. And also, interface requirements to users are called user interface requirements, which are probably the most difficult ones to get right. User interface requirements often appear in requirements documents. What they need to do is define what content is on each screen, but without defining what the screen actually looks like. Defining what the screen looks like is a design issue. This does not happen at this stage, it happens later in the process. But what we need to do is give the association between a functional requirement and what the screen content is going to be. So quite commonly, the UI requirements will be in the form of some form of wireframe diagram. These are not confused with the final appearance of the screen. They just simply show you what information needs to be captured on the user interface in order to execute the functional requirement. Integration requirements. These identify all the sources of inputs and all the destinations of outputs. So every single source or destination needs to have its input and outputs defined. We need to know what type of data is flowing across the connection. Are there any protocols? Are there any particular data transmission rates? What kind of volumes are being stored in databases? What kind of network access do you require? What kind of network speed do you require? If you're integrating with third-party requirements, you need it to be well documented to make sure that all the interfaces are completely defined unambiguously. And it should be stated in the architect specification, not in the requirements. Architecture is all about how things fit together, which is where this information really belongs. Performance requirements are important for specifying the behavior of the system. So, for example, capacity. How many concurrent operations can happen at once? What is the data capacity of the system database? We've got availability. Certain metrics are available for availability. We have the mean time between failure. What is the average time between two things going wrong? What's the mean time to restore? How quickly can we get the system back and running? And availability is that fraction, that equation. We also have response time. So what is the time difference between an input arriving and the output being delivered? We've also got throughput, which is a measure of how much data is actually being passed through the system in a given time interval. It also must occur without any errors, without data loss, and within the time required. Any system has assumptions. So what's an assumption? It's something that's taken for granted. It's something that's stated as true without any justification, really. So assumptions are often not stated, which is always a bad thing, because if something is assumed and somebody doesn't make the same assumption, then we're going to have problems. So one important thing is when we're looking at requirements is to find the assumptions, even if they're not explicitly stated. State them and justify them. Assumptions are absolutely everywhere. We must make sure they're all well documented and justified. Jargon is an interesting concept. The idea of jargon is it's a language or a subset of a language which enables people within a particular domain to communicate accurately together. Natural languages such as English are notoriously ambiguous. If you insert a comma into a sentence, you can completely change its meaning. This is why in the legal profession they do not use commas within legal documents. A misplaced comma can change the meaning of the sentence completely with dire consequences. The important thing is it's for people within the same domain to be able to talk unambiguously, so a particular term means something very specific to that domain. To give an example, in the English language there's two words which are often confused by many people, which are jealousy and envy. Many people say, if you say I'm going on an exotic holiday, oh, I'm jealous. No, they're not, they're envious. Envy is somebody having something you wish you had. Jealousy is when something you have you like, you're wishing. Jealousy is when you have something which you are frightened of losing. People often get the terms wrong. Now, another issue is slang, which is quite the reverse of jargon. Slang is a language between peers which enable them to communicate with each other in public without anybody else outside their peer group understanding. So it's important that jargon is used correctly. Developers must think in the domain to communicate with others, but only use the jargon within the audience that understands it and not people who don't work within the same domain as you. How do you measure the quality of requirements? Well, there's a number of metrics, and it's getting the balance right. So importantly, requirements are completely separate from design. Design is a separate phase. Requirements need to be testable. That's very important. Requirements need to be complete with no omissions. Requirements need to be clear, explicitly stating exactly what is required for this system. They need to be consistent. We don't want two requirements which say something which are completely different to each other. And they need to be traceable to make sure that every requirement has actually been implemented in the final system. Almost by definition, most requirement documents, if not all requirement documents, have got inconsistencies or have got omissions. One important thing is never try and resolve the issues without consulting the customer or business analyst that's responsible for the system. A good way of resolving these issues is to conduct an interview with the subject matter expert involved. It's very important when you conduct an interview, you have a very good understanding exactly what you need to know and what information you need to extract from the subject matter expert you're going to interview. There's several different ways you can conduct an interview. You can have a structured interview. You can actually write the questions in advance and maybe share it with the SME in advance. If you do that, it's like a script. You need to stick to it. It's good for surveys, not so good if you're not really sure what you're trying to find out. The unstructured interview is for that second scenario when you're not really quite sure where we're trying to be or what information you need to have. So what you do is you start with various questions which gets the interviewee talking. When they start to respond, you pick up on phrases they say and qualify them with further questions. It requires more skill to achieve this, but can be much more productive in the long term. You can also have different types of questions, open questions. There is no right answer. You're just probing really to see what the SME comes back with. Closed questions require a very specific answer to a particular question. So some ideas for questions. Situation questions. Why do you want this problem solved? Why do you want this particular solution? What are you thinking about? What are you trying to achieve? Problem questions. You've got a problem. What problem do you want to solve? Implication. What's going to be the impact of this solution? What is the business benefit of building this solution? And we also need to have the payoff things. What are the priorities? Which piece of functionality are going to be more business worthwhile than the others? Which ones are going to generate more revenue than others? So now we're going to talk about architecture, which is how things join together. How do systems communicate with each other? There are different definitions of architecture. defined by different organizations. In UML, the Unified Modeling Language, it's the collection of connected units which are organized to accomplish a specific purpose. And what you need is some kind of model which defines how these things interconnect. The IEEE says a system is a collection of components which need to be organized to perform a particular function or set of functions. And software architecture in practice says the software architecture is a program, is the structure, or the structure is a program which enable the elements to be connected together and the relationships between them. So what are the goals of architecture? Well, it involves various people, various parties, the stakeholders, the business goals as well, and also the IT infrastructure which needs to support it. As DevOps, the IT infrastructure is the most important aspect of it, but there are the other two to take into account. As DevOps, we'll be concerned with building the infrastructure to support the architecture that's required. So, an IT architecture, what is it? Well, it's rules and guidelines and patterns of system development. So we've got to manage the problem as a series of discrete pieces. We need to define the communication interfaces between the pieces. We need to think about the overall structure and how data flows. We need to integrate the various systems and subsystems in the environment together. We need to develop software modules on the best possible design practices and design patterns. We need to control the delivery of software into the system environment effectively and efficiently and reliably. So this compares architecture and design. Architecture is more strategic, whereas design is tactical. The important word in architecture is how. How do things fit together, rather than what do we use to connect things together. We look at programming paradigms and architectural patterns, high-level patterns, rather than algorithms and low-level patterns. We're looking at the non-functional requirements. Architecture is a non-functional requirement. It's a statement of these systems are going to communicate in this way, whereas design is concerned with the functional requirements. What does the system actually do? And in UML, the diagramming language, we have certain diagrams which are more associated with architecture than those that are used for design. So let's look at some architectural patterns. The client-server architectural pattern has been around for some time. The idea is we have a thick client which communicates across a network with some external data storage. The thick client has the user interface, the business logic, and the data access layer all in the same unit of functionality. So the advantage of this is we basically separate all of the code from the data. It enables the server components to be reused. The server components are managed in some central location, and we can optimize the use of infrastructure. It's also quite scalable. So the advantage of this is we basically separate all of the code from the data. It enables the server components to be reused. The server components are managed in some central location, and we can optimize the use of infrastructure. It's also quite scalable. The problem is it doesn't work well with the requirements changes. There are security issues as well associated with it. The server is a single point of failure, which means the whole system becomes unavailable if the one component fails. We've also got the presentation and business logic in the same place, which is not a good idea. It's also quite difficult to test and scale in terms of the thick client. Another pattern which is very popular is the n-tier architecture, where n is a number which is usually 3. The great advantage of this is it's completely multi-threaded, so the middle layers can be executed in parallel, so multiple clients can each have their own threads executing it. If the business logic changes, we don't need to change the user interface client code. Typically the client is a very thin client, such as a web browser. We reduce the network traffic dramatically because most of the network traffic is happening between the layers. And we can add additional layers or tiers for various purposes to add layers of abstraction and failover. The disadvantage, if requirements change, we need to change quite a bit, maybe in the middle tiers. The security implications are quite interesting as well because there can be problems associated with the access from the external sources. We've still got server availability and reliability issues, and we've still got testability and scalability issues. Service-oriented architectures are becoming increasingly popular. They have a great number of advantages. Probably the most important one is loose coupling. We have components which can be written in different languages, operating in different environments, which can communicate with each other seamlessly without having to worry about the details. We've got business services can be spread across lots of different platforms, and you just use the service you need as and when you need it. We don't need to know where anything is. It can be anywhere within the corporate network or within the cloud, and we don't need to know the exact location because the infrastructure takes care of it. We can reuse services. If you've got a legacy application, what you can do is put a service-oriented front end on it, and then it becomes part of a service-oriented architecture. It reduces development costs and increases development speed, and it's easier to integrate the business and the IT environments. There are some disadvantages. It's quite difficult to migrate because there are so many moving parts. You need very good control. You need very good auditing and monitoring systems. And probably the hardest one is getting the development and design correct. How do the pieces fit together? How do they communicate with each other? What series of operations is required to achieve a particular business goal? Many people and organizations these days are going towards REST microservices. It's a good foundation for many API designs. REST is actually not a new idea. It's been around since 1996 when the HTTP protocol was first devised. Basically, the World Wide Web is a good example of a RESTful service. So the architecture has evolved over time. The web itself has evolved massively over the 20 years it's been in existence. It focuses on resources and information and not code. What you do when you talk to a REST service is you ask for a representation of information, not for the actual data itself. So components can evolve separately. It's very highly scalable. You just add other services. Development costs is greatly reduced because each piece is a fairly small unit of functionality. And it makes data important. It exposes data as a resource and requires a separate way of representing data. The data and the code are not considered connected. The data is stored somewhere in some form. The code delivers the data in some representational form. The disadvantage is a lot of people are not familiar with the approach, and infrastructures are not really geared up to deal with it, although that is getting better. It also requires a very significant change in the way that developers think about how things interoperate. Another architectural model is the 4+1 view, which is quite an interesting concept. The idea is that different people and teams have different views of systems. So, for example, you've got the logical view is how the end user sees a system, which is in terms of its actual functionality. You've got the development view, which is how developers see it. What are the actual software components and how do they interact? You've got the process view, which is what are the actual processes and how do they communicate with each other? And you've got the physical view or deployment view, which is where the software actually resides on what hardware and what location. And so each of those four views gives you a slightly different picture of the system. So the 4+1 architectural view says, okay, we'll take these four views and then generate the fifth view, the +1, which are the use cases which take the solutions from the four views and combine them together into a single view in terms of use cases. User acceptance tests are very important. So having gone through the requirements analysis to decide what we're going to build, we need to decide, have we built the right thing? So user acceptance tests are a formal set of tests which are performed on the end system to prove that we've actually built the thing that the customer actually asked for. So have we actually implemented all the functional requirements correctly? So we need acceptance criteria. Does it solve the problem? Does it interact with all existing systems? So basically, the functional requirements drive the acceptance tests. From a functional requirement, you can design the test cases. And once you've designed the test cases, you can write the tests and perform the user acceptance tests. Functional requirements are written very early in the development process of a new system. The user acceptance tests should be extracted directly from the functional requirements at a very early stage as well. They're actually applied, of course, at the end of the project once the system is complete. So how do we do user acceptance testing? Well, first of all, we need a test bed. Ideally, this should be a clone of the production environment. Any changes in the production environment get mirrored in the test bed. This minimizes the risks of compatibility issues. If we have a system that passes the acceptance tests and then moves into a production environment which has changed, then it's not going to work in production. We may need to make compromises to satisfy various constraints. We probably can't simulate the large number of remote users our system may have. We might not have any users at all. We need to concentrate on functionality and information flow. We're not interested in performance at this stage. Performance is only assessed once the system is effectively in pre-production. We will probably have to simulate external systems. We almost certainly will not be able to talk to other systems, particularly if they have an impact on the real world. We should also have databases which are populated with recent production data. We almost certainly will need to sanitize the production data to remove sensitive information, such as telephone numbers and email addresses. So one example of doing this is to replace all customer names, some name like John Doe, which is not going to have any impact. Very important about telephone numbers, email addresses, because you can inadvertently cause. You have to be very careful about sensitive information such as telephone numbers and email addresses. I've known one organization where they inadvertently released an offensive email from the development environment to 500 real customers due to a configuration error and using a production database copy. Use cases are a way of documenting requirements. If you have a structured use case, it looks rather like a test case. If you think about it, a use case consists of the steps of initial conditions or preconditions, inputs from users or other systems, the expected outputs, and the final conditions or post-conditions. These are actually the same steps and operations which are involved with testing. So effectively, a use case can be replaced by an acceptance test, or rather, a use case can be converted into an acceptance test. If the use case says customer selects a product code for purchasing at the current market rate, the user acceptance test must specify what the product code is and what the current market rate is so that you can perform the test correctly. So the designer of the user tests must establish initial values for all of the database elements at the start of the UAT. Effectively, the database must be in a well-known state before any tests are executed. You also need to know what the execution sequences of use cases are. Each use case performs a particular functional requirement. Typically, a use case cannot be executed in isolation. For example, many systems have a login use case. None of the other use cases can be used until the login use case has been executed. You must specify the values of all inputs in all steps. The data values in the outcomes must also be specified for each use case step. You also need to know what the final state of the database will be at the end of the user acceptance test to know that the actual system performed correctly. You will also have additional details in the design. You'll have screen layouts which will include data formats. You have instructions for how you enter the input and in what form. You also have to have the users trained in advance of a UAT. The users must know how to execute the UAT seamlessly and correctly. So we have a combined set of things, the use case scenarios, the database and transaction values that produce the user acceptance test scenarios. Now, an important thing is that for every functional requirement that we have for our system, there needs to be a corresponding user acceptance test. How do we ensure this? Well, a good way of doing it is using traceability matrices. What you do is you draw matrices where you have the use case requirements on one axis and you have the tests from the UAT on the other axis, and you put a cross where the test actually tests the requirement correctly. Then what you do is you look for gaps. If there is a row or a column without an X, it means there's either a requirement without a test or a test which is superfluous because it doesn't test a requirement. If we're doing agile software development, we have user stories rather than use cases. So the user stories need to be testable. So how do we have a testable user story? Well, it needs to describe an action of use to a particular user. So the story will say, as a customer, I want to do this. You specify the exact target user or role, so it needs to be very specific about what role is going to be executing this story. It needs to have very clearly stated acceptance criteria. In other words, it needs to be very testable. It needs to be small. Typically, a user story should be implemented in a fraction of a day or at most several days. The longer a story is, the less control you have over it. It needs to be short and precise, very few words that describe things completely. So here is an example from the case study we introduced earlier. The question is it testable and can it be improved? This is a typical user story notation. As a Docker administrator, it's specifying the role correctly. I need to be able to attain a list of all containers that terminate in the last hour, a specific statement of what's required. The output web page needs to contain the event type, the container name, and the date and time of the event sourced in reverse time order. That is giving a test. That statement is giving acceptance criteria. It could be improved, but it has the basic ingredients. So that is lesson 1, and here are the key takeaways. DevOps is a blend of development and operations which requires a cultural change to improve quality and reliability. There are many technical challenges facing DevOps, mainly changing technical environments. There are a large number of categories of software tools, each with a large number of choices. We need to select wisely. Cloud computing eliminates the need for expensive data centers and the associated support groups. Information security is vitally important for protecting sensitive assets. It needs to be engaged very early on. Architecture describes how systems communicate and interact together. It is very important to ensure that requirements are complete and consistent. Don't fill in the gaps. Ask an expert what is required if you find a missing functionality or an inconsistency. User acceptance tests are essential to ensure that all functional requirements have been correctly implemented. That's the end of the session today. Thank you very much.